Okay, new chapter, chapter 14, vector valued functions. All right. So to recap, what have we done? We studied vectors and some fun and play with vectors, sketching vectors, and we learned about some surfaces in space like planes and spheres, as well as quadric and cylindrical. And we also looked at the parametric equations for a line in space. That was important. And how you represent that. And we did some other stuff too. I'm trying to keep it down to 25 words or less. So now we're going to move on. Now, don't forget all that stuff in the previous chapter because we're building on that. Now you know all those basics. Those are going to become the building blocks for what we're going to study next. And so this next chapter is all about vector valued functions. And you may go, well, what the heck is that? And that's what we're going to define first. So I'm going to start us off easy. Okay. Let's do a definition of a plane curve. Plane means 2D. So I claim that you've already studied this in Calculus 2 when you studied parametric equations. You did this already. You may have forgotten, but here it is. If you have two equations where both x and y are given as functions of a parameter, typically t is very common because t stands for time, and we use a lot of these parametric equations to model motion in both 2D and 3D. So x is equal to some function f of t, and y is equal to g of t. Fine. And t is typically time. Not always, but typically. Now, a space curve, so now we're looking at 3D, is a set of all ordered triples now, f of t, g of t, h of t, where your parametric equations are x equals f of t, y equals g of t, and z equals h of t. Now, this is, folks, these parametric equations have to be taken as a group. You can't pick and choose and go, well, I just want one of them, or I want 2 out of the 3. You don't have that choice. They come as a set. And when you studied parametric equations back in Calculus 2, and I know some of you may not have, depending on what school you studied at, but here at Southwestern, you stuck to 2 dimensions, but these parametric equations came as a set. So same type of thing. Now, let's take a look at this new type of function called a vector valued function that's going to basically spring from these parametric equations. Okay. So before I do this, I want to do some review. Really, this isn't in your course reader, so draw a function machine for me. Here's a picture of a function machine. And you did functions in algebra and pre-calc and trigonometry and calculus. So you know some things about functions. So I want to make sure you have that down before I introduce a brand new function. That's all. So the review would be, let's say you had a function y equals f of x, okay? And you feed it some input and it gives you some output. Now, what kind of input are you giving this function of a single variable? This is known as a function of a single variable. It turns out you feed him his input, which is x, which is a real number. You know, you feed the function x equals 2 or whatever, and then y equals f of x, whatever that is, could be like y equals x squared, and then he poops out some y value, and that would also be a real number. Now, the way you would graph this function of a single variable is you would take the input and the output and create an ordered pair out of it, and then plot the ordered pair points in 2D and then connect the dots. And that's how you would graph a function of a single variable. And I hope you all are okay with that. Yeah. No, nothing new. Okay. Welcome to a completely different kind of function, folks. Completely different. So here's the function machine. We'll still have a box here. Let me have a little spout for his input. And let me have another spout for his output. Okay, the input here is t, and t typically represents time, but it doesn't always have to. And time will be a real number, like time is equal to 3 seconds, you know, boom. Now, your vector valued function, and remember, you want to have correct vector notation, so there's boldface here. is going to be given with angular brackets here, and the two-dimensional version will have two components, or the 3D version will have angular brackets f of t, g of t, comma, h of t as the component. So it depends on if you have a 2D or a 3D vector valued function, and we're going to be dealing with both this semester. Now here's the weird part. The output is not a single real number like you're used to. It's going to be a vector. That's right. So when you plug in your time t equals 3 seconds or whatever, the f and g, and if you have h, will grab the t and then itself process it and give you some vector with some components. I'll just give it some bogus components there, a, b, c. We'll do a 3D version. And down here is the definitions where they're showing you, here is the vector valued function written as linear combinations of I, J, and K, or you can give the vector valued function in component form, whichever you prefer. Now, you know me, I prefer component form, and I've told you already why I prefer it. However, the physics folks tend to like the I, J, and K format when they're representing their vector value functions. Okay, and we'll do both in this course, just like we do both for, you know, vectors with scalar components. So why vector valued functions? Like, who cares? Well, as I mentioned a couple times already, they're used to describe motion a lot. Okay. So by letting this parameter t represent time, you can represent motion along a curve, and it could be 2D or 3D. Okay. Now, how do you graph a vector valued function? Well, very carefully. For every time t, you would get a vector. So you graph a whole bunch of vectors here. And now here's the weird part. In order to actually get the graph of the vector valued function, I mean, you're going to get a whole set of vectors. You don't look at the vectors when you're looking at the graph. You look at the tips of the vectors only, and you erase everything else. You get rid of it. And then you connect the dots of the tips of the vector. So anytime somebody says, hey, go graph this vector valued function, you don't really see the real deal. You don't see the collection of infinity vectors because somebody erased them all and just kept the tips and connected to the dots of the tips and then got their curve. Okay. And the thing about these curves is they do have an orientation to them, and that means that they have a direction. So like this curve looks like it's moving that way. What does that mean? Well, as time is increasing, that's the parameter t, the curve is going that way versus the other way. So anytime you're asked to graph a curve from a vector valued function, you have to put at least one arrow in there so somebody can see the orientation or the direction. Okay. Let's sketch some two-dimensional vector valued functions. If you had me for Calculus 2, and I know there's a couple of you in the room who have, you've probably seen this lecture already. What? Yeah, because I did it for you back in Calc 2. For everybody else, don't worry. I'm just going to do this all over. If you have a graphing calculator handy, I encourage you to grab it, because we're going to go over a little private lesson here on how to use your graphing calculator to graph two-dimensional vector valued functions. You're just going to basically use your Calc 2 knowledge, and the components of the vector valued curve are your parametric equations. And then you just type those into your calculator and then hit graph. Now, when you have your calculator handy, you want to make sure you're in the correct mode, because usually you graph in what I call function mode. So if you hit your mode button here and this menu comes up, down here about the 5th row down, it says the words function, parametric, polar, and sequence. Right now I was doing polar, I guess the last time I graphed this, which I don't want to do now. Use your arrow keys to go down to the function row, move your cursor to parametric, hit enter to actually choose it. That's what we're going to do, parametric, and then quit out of here. I'm going to hit second quit, and I'm out of there. Now what? Go to your gray button up here, y equals, and you'll notice you have an x1t and a y1t. So those are the parametric equations that we're going to graph. I'm going to hit clear because it looks like I was graphing something else the last time I was here. I have no idea what I was doing. And then I'm going to go t squared is my first parametric equation. And then the other parametric equation is t, so you just hit your x button here, t cubed. Now don't hit graph yet because you want to make sure that you're going to graph the whole picture. So you want to go into window here, hit your window key. And right now I'm, see where it says t minimum is 0 and t max is 6? If I use these as my range of time, and I'll even hit graph just to show you the problem. And there is a piece of it. That only gives me half the curve. Doesn't give me the whole picture. So you have to be careful. It would have been better had I had my t minimum be -10. And let's have my t maximum be +10. That's usually my go-to default. -10 seconds up to +10 seconds. Hit graph. And notice there was an orientation. It looked like it sketched it coming from the bottom and then going up. And that's kind of a neat graph. And so, wow. So it looks something like this. And I'm going to put an arrow on there to indicate the orientation. Okay. Here's a parametric equations, but that's a vector valued function there. Very nice. Let's do letter B. Uh-oh, we have trig. So if you are asked to graph anything with trig in it, and you're using your graphing calculator, I encourage you to make sure you double check that your mode is in radians. Otherwise, it won't graph anything at all. It would look like your calculator is broken. And oops, I'm in degree mode, not good. So I need to go down to that row and make sure I choose radians so that my graph will be okay. Quit out of here, go to y equals, hit my clear key a couple times. I don't want these anymore. My first component of my vector valued function is cosine t. And then drop down to the other parametric equation. I got sine t, fine. I go to your window again. I can graph -10 to 10, but that actually makes the computer work way harder than it has to. Because for this particular curve, I really only need, it's going to be a circle, time to go from 0 seconds to 2 pi, believe it or not. And that's going to be enough. So when I hit graph, don't blink so you can see the orientation. That looks like an ellipse, but that's because we're not in the z square. It's really a unit circle. And I think it was oriented in a counterclockwise orientation there. So if I go over here, yeah, that's a pretty sad circle. Okay, but there you go. And what about this letter C? I still have sine and cos for components, but it looks like x is sine and y is cos. How is that going to be different from letter B? Check it out. What's the difference? Anybody know? Oops, wrong place to go.
Maybe a different orientation.
Good. Yes, it's still going to be a unit circle, but it's going to be oriented clockwise, I believe. Let me hit it. Yep, there he is. Isn't he cute? Okay, so go back to your paper, draw that in there. Hopefully you're taking good notes. Okay, now the next few examples we're going to do a little bit harder. And this is the kind of stuff I do put on, quizzes and exams. But you did this already in Calc 2 also, or you were supposed to, but maybe you forgot. I don't know. So we're going to sketch the curve again, but now we're going to do a little extra. The little extra is we're going to eliminate the parameter. That means get rid of the t, and try to rewrite the components of your vector valued function as a single equation, a single rectangular equation with x and y. Okay. And those better match. So let's first graph with our graphing calculator the components t squared minus 1 and t. Okay. t squared. Oops, I forgot. I had to do a -1 too. Sorry, -1. And then the other component was just t. Go back to your window because you may want to change your t minimum back to -10 seconds so you capture the whole picture. Otherwise, you only get a portion of the curve. So when you graph this baby, woo, yeah, that looks like a sideways parabola, doesn't it? Mm-hmm. Mm-hmm. Nice. So you're going to go. Remember, this is representing motion. So if this vector valued curve were representing, say, a bug that was walking on your table, you know, walk, 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 walk. And what's going on here is at any moment of time, you could go, well, at time t equals, say, 3 seconds, what is the location of the bug on my table? Well, you would go, well, time t equals 3, plug that into your vector valued function. V of 3 would be 3 squared minus 1, 3. And I get 8, 3. So way out here at position 8, 3, like right there at that point, your bug would be located at the point 8, 3 at time t, excuse me, equals 3 seconds. That's sort of the idea of this. So you can get that flavor of motion. Now, what about eliminating the parameter? This problem is ridiculously easy, but I want to start with something easy. So you first write out your vector valued functions components separately. So you've got the x component is t squared minus 1 and the y component is t. And then you look at both of those and you go, which one of those equations is easiest to solve for t? And it turns out the second one, because it already is solved for t. Ha ha ha. T is equal to y. Oh, okay, then what? Then you substitute that into the other equation. So your final answer, when you eliminate the parameter for this case, is x is equal to y squared minus 1. And now you do a check. Is the graph of this single rectangular equation the same as this sideways parabola? And I claim it is. So we've got a winner. Same graph, everybody's happy, and we win. And so we got a single rectangular equation where we eliminated the parameter. And we're done with that example. Let's do one that's a little harder. So in letter E, we have this vector valued function with some nice components. So I'm going to go back to my calculator just to see what the graph looks like. Real quick here. And I think you can do this in GeoGebra, but I always forget how to do parametric equations. So you may have to Google it up, but it's not that hard. You can do graphing these curves. And so you can even do 3D as well, which is kind of fun. So I need to do a square root. So let's see, square root of t here. And then 3 minus t is my other component. And let me just check my window. Now here, even though I have t going negative, it won't accept it. Why not? Because you can't take square root of the negative. It won't give you an error, surprisingly. It'll just let you do it. It just won't actually plug it in to, any of the components. It'll probably start at where it's allowed to start. We're going to talk about domains in a moment at t equals 0. So technically, I should change this t minimum to 0 because he can't eat anything that's a negative number. And then when I hit graph, let's see what happens. Whoa, I get half of a parabola. And it looked like it was oriented downward. Okay, so yay me. So something like that. Now, great. Let's go eliminate the parameters. So first I rewrite this where I get my components written out. X is square root of t, y is equal to 3 minus t. And now here's the part where you may go one of two ways. I'm going to go the way that I don't get two different equations. I'm going to solve x equals t for t. So what happens is I'm going to square both sides. And I get t is equal to x squared. So okay, so now what? So you're going to substitute that in place of the other equation's t. So I get y is equal to 3 minus x squared. Now, here's the problem. If you graph y equals 3 minus x squared, does that graph match what we have exactly? Yes or no?
No.
No, it doesn't, because that would be the whole parabola. Thank you. Yeah. And we don't want the whole parabola. So here's what we're going to do. You have to add a little extra. We're going to need to restrict the domain. What do you mean? Well, I'll keep the y equals 3 minus x squared. And then how do I basically tell somebody, look, I only want the right half. Erase the other half of that parabola. You know, we don't like that guy. So you do this. You say, as long as x is greater than or equal to 0, I've restricted the domain, and now the graphs match. So those two things together give me the final answer for letter E. Okay, so there is a different way of doing this that I'm not really happy with, but sometimes my math lab lets you do it. But on like exams, I'll probably take away points. What if instead of solving for t with the first equation, which we did, and we got t is equal to x squared, you solve for t with the other equation? Okay, so I'm going to add t to both sides and then subtract y from both sides, and I get t is equal to 3 minus y. Okay, in this case, we're going to be okay. And then you would put that into your equation, okay? And that should work, we hope, for this one. Okay, so you're going to get x is equal to square root of 3 minus y, which it's okay. You know, it's a function of y now instead of a function of x. Okay, let's do some more of these, and then we're going to go backwards, where we're given a rectangular equation and we have to come up with the parameterization. And that's going to, skill is going to be needed late in the semester, probably in November. So we're planting a seed for later. So if you have your graphing calculator here, and I'm going to start going kind of quick, how would you graph those and eliminate parameters? What do we got here? 3 cos t, 4 sine t. Okay, go to your window. I think 0 to 2 pi is good. Do a graph. Woo! And it is an ellipse. Oh yeah, this is not a circle. This is an ellipse this time. Okay, so then how do you eliminate the parameter? And it looks like it was going counterclockwise, this ellipse. That's the orientation. So like, and what are the intercepts? It turns out 4 is the y-intercept, 4 and negative 4, and 3 and negative 3 are the intercepts for x. So it's going to look like that. So how do you eliminate the parameter? This time you have to be careful. You don't solve for t. I don't want to see any arc sine or arc coses in here. That's a hot mess. So what you're going to do is you're going to use this handy fact from the past. Cos squared of theta plus sine squared of theta is equal to 1. I'm sure everybody in the room has seen that sometime or another in your past mathematical education. Okay, so how is that equation going to help us? Well, not yet. I'm still going to write out x is equal to the x component here, 3 cos, and y is equal to 4 sine. And now, instead of solving for t, you're going to solve for the trig equations in turn. So cos is x over 3, sine is y over 4, and then you're going to basically plug these into this trig identity. So you're going to get x over 3 squared plus the quantity y over 4 squared equals 1, and then clean this up just a little bit, and you're pretty much done. And this is the standard equation for an ellipse centered at the origin. You probably remember this from your pre-calc days. And so that's a match. So we like it. That's the answer. We eliminated the parameter. Needed the trig identity. And there's another Pythagorean trig identity you may need that involves tangent squared and sec squared. So when you're doing your homework, go look that one up and keep it handy for another type of problem similar. And last but not least, my grand finale I love this one because it's not in the text, but there's stuff like it in there. So this is kind of cute. And I give this to my Calc 2 people too. So if you took me for Calc 2, you've seen it. So t squared minus 2 is the x component. And then the y component is 2 minus t squared. Okay, fine. I'm going to go to my window. Let's make sure we've got everything here. I'm going to do something weird. I'm going to go from negative 10 to positive 10 at first. And you're going to go, Okay, and it's a portion of a line. But what was the orientation? Was it going upwards or downwards? Did you catch it? So watch this. If I have T minimum stay at negative 10 seconds, but I change my T max to 0, and that's it, watch the orientation when I hit graph. It goes coming from below upwards. But then if I go back to the window and change my T minimum to 0 and my T max to positive 10, watch what happens. Ooh, it went the other way. So it's going to go both. Exactly right. Can you do that? It's going to go both. So this is rare to have a curve that's got the orientation both ways. Okay, now where does it cut off too? So it kind of goes up, this way, and then it makes a U-turn and goes back the other direction. So how can you figure out the U-turn? Well, it turns out if you plug time t equals 0 seconds into your vector valued function, you'll locate the position of that point where the U-turn occurs. So plug t equals 0 into there, and t squared minus 2 would be negative 2, and then 2 minus t squared would give you 2. So at the point with coordinates negative 2, positive 2, this thing turns around and makes a U-turn. Pretty cool, huh? How do you eliminate the parameter? Okay, first write down the equations, the parametric equations, essentially. Now you can solve for t and then plug that into the other equation. But I want to make this really easy on myself. I'm noticing that both equations have a t squared in it. Okay, so how about instead of solving for t, I just solve for t squared. Let's make this really easy. So when I solve for t squared with the x equation, I get t squared is equal to x plus 2. And then I'm going to substitute that in place of the t squared for the y equation. You have to be careful because parentheses matter. You're going 2 minus t squared. The t squared is x plus 2. And then you want to distribute the negative over parentheses. And so when I do that, I'm going to get y is equal to 2 minus x minus 2, but then the 2's cancel. So all you're left with is y equals negative x. Now, this is the time when you match or you try to match. Does this graph match the graph of our vector valued functions curve? Exactly. And I claim it doesn't. Because y equals negative x, that would be an entire diagonal line. But our vector valued function didn't have the entire line, y equals negative x. It kind of went up to this point, negative 2, 2, and then hooked a U-turn and went back down. So we're going to, again, restrict the domain. And we're going to say, okay, it's y equals negative x as long as x is greater than or equal to negative 2. Now we'll have a match of the graphs because we'll erase the portions of this graph, this diagonal line, as long as x, if x isn't greater than or equal to negative 2. We'll take care of it, get rid of it. Okay. So now let's go backwards and parameterize, and then we'll discuss a little bit of domains, and we'll pick up domains next time in detail, but I want to start it so we can at least get that down. Next time, after I finish domains, I want to get into limits and limits. And then we're going to do derivatives and integrals on Friday. Okay? Good times, people. This is the calculus. It's going to hit. It's coming. So if you feel like you're still a little rusty on those derivatives and integrals, now's the time. Prepare. So these examples here are where you go backwards. So somebody gives you a single rectangular equation, you give me a vector valued function. And I claim it's super easy as long as you follow my 3 rules. Rule number 1, is it a function of x? And y equals x cubed is indeed a function of x. So the rule for functions of x are you let x be t, and then y is whatever. In this case, x cubed plus 1 would be t cubed plus 1. So the vector valued function, and make sure you use vector notation there, the little arrow over the r, equals angular bracket t, because that x is equal to t, comma t cubed plus 1. And there's your answer for this first example. I'm done. Yeah, and the graphs will match. Don't worry. Second rule, what if you have a function of y? In this case, this equation here, x is equal to y squared minus 4. That's a function of y, not x. So a function of y, the first thing you're going to do is you're going to let y equal t. Okay. And then x is equal to t squared minus 4. And then you start writing up your vector valued function, r of t, and you put a little arrow on top of that r for me, please, equals angular brackets, x is t squared minus 4, comma, and we let y be equal to t. Now put a box around that, and there, we just came up with a vector valued function that goes with that equation. We're done with that little problem. Now the hard part. What if it's neither a function of x or y? In fact, when you graph this, it's a circle, and circles don't pass the horizontal or the vertical line test. So it's neither a function of x or y. And this is where it gets hard to parameterize. Sometimes people spend a lot of time figuring out how to parameterize curves.
You could divide the left side by 16, right?
Mm-hmm.
And then, it's turn x into cosine t and y into sine t.
You're on the right track. Congratulations. It'll work here. Now, will that work for every single curve? No. In fact, my master's thesis many years ago, it was all about parameterizing a curve of infinity length, a fractal. Yeah, it was crazy. Okay. So it wasn't straightforward. But yeah, Lupe is on the right track. So you're going to get this. He's seeing that it's a circle, but we'll look at that one problem we did back here when we used this trig identity, and we'll use that to help us get the parameterization here. So we're parameterizing x squared plus y squared equals 16. After dividing both sides of the equation by 16, as he suggested, I then have an equation that looks like x over 4, the quantity squared, plus y over 4, the quantity squared, is equal to 1, like that. Everybody see that? Now what? Now, when you look at this trig identity, cos squared theta plus sine squared theta equals 1, you're going to use that to help you finish out. You're basically saying that cosine theta is equal to x over 4, and you're saying sine of theta is equal to y over 4. And now you solve these two little equations for x and y. So you get x is equal to 4 cos theta, and y is equal to 4 sine theta. And then if you put this into a vector valued function, instead of t, you're using theta. Well, what if I want t instead? I don't care, as long as you have a parameter. Let's just use theta to be different. So your r of theta this time will be angular bracket. The first component is 4 cos theta, comma, and then the other component would be 4 sine theta. So your parameter here is not t, but what if you're like, well, I like t better. I don't like theta, or maybe MyLab Math says they want t. No problem. Tell them no problem. We satisfy all customers here. Then just take the theta, get rid of it, and replace it with t everywhere. You know, we're fine with that. Okay, fine. That'll make you happy. All right. But I don't want you to get addicted to the letter t, where every time somebody is talking about vector valued functions, I don't want you to go off the rails if it has a different parameter other than t. It's still going to be legit. Okay. Now, quick review question before we do domains. What if somebody wanted you to sketch this vector valued function without sketching it? Like, don't go to GeoGebra or anything, okay, folks? Just look at it, look at the components, and if you had to, write them out. Like, what is x equal 2 plus t, y equals 3 minus 4t, and z equals -1 minus t remind you of? I'll give you a hint. It's something from chapter 13 that we studied already.
Is it like the standard? No.
The general plane or something like that. It's like a plane equation.
These are the
Yeah.
parametric equations for a line in 3D.
Oh yeah, or line.
yeah.
Be careful, lines and planes are two different animals. That's a line. So it would sketch as a line. Be careful, not a plane. Planes are different. Okay. With vector value functions are curves and a plane is a surface. So the difference between curves and surfaces is a distinction that it would be good for you to make early to make sure that you don't blow the other things we'll be doing this semester. But I have a type of software that I got many years ago, and what I like about it is it lets me graph curves and easily, and I'm pretty familiar with it. So like if I wanted to graph this vector valued function where the first component is 2 plus t, the second component is 3 minus 4t. I'll show you what I'm doing here. And then down here, down here would be -1 minus t, and then I go hit it. I may only get a piece of it. Okay, it's just showing me a piece of it. It's a portion of a line in space. Oh, there it is, that purple thing there. I could do my, where are those parameters? So if I go to my parameters, oh, there it is, and I ask for a little bit more x, y, and z here. I want -10 to +10. Yeah, that's the ticket. Maybe I'll get a little bigger portion of my line in space. That's what I want. Let's see if it'll do it for me. Ah, there we go. Oh, no. Okay. Let's see if it'll rock and roll for me here. Come on, baby. Nope, now it's going back to only a little tiny piece. Oh, bummer. I'll have to play around with this a little bit. Okay, so this software is kind of neat because what I like about it, for those of you who are into graphing, you can graph polar curves or whatever you want here. So this is a nice piece of software. Like I could go R is equal to theta. And for those of you who are in the polar, and we're going to get in a polar later, not so much now. Don't worry about it too much now. But that's kind of a cute polar graph, isn't it? Kind of looks like a, I don't know, spiral. Okay. Back to reality. Let's do a little bit of domains. Okay, we're still not into the calculus. We're talking about domains. Now, you studied domains in an algebra and pre-calc. Really? Yeah. What are the okay inputs to a function? What can you feed a function? And so I put together, when I taught pre-calc, I put together my rules and regs for domains, and we're going to just follow my pre-calculus rules and regs. And so here's how we'll change it up a little bit to deal with vector valued functions near the end. You'll see. So first, you're trying to find all the values of time t that the vector valued function is allowed to eat without dying. Okay. So first, just assume all inputs are okay. Assume he doesn't have a restricted diet. He can eat any value of time t that you feed him, negative, 0, positive, whatever. Now, you start to worry with the next few questions. Here's the first question. Do any of the components have a denominator in them where the denominator contains the variable t? And the reason why you're scared is you want to eliminate any value of t that would make a denominator equal to 0, because you know dividing by 0 is not okay. So we want to eliminate any values of time that would make that happen for us, because those would be bad. Okay. Another thing we're going to have to restrict the diet for is, are there any components in your vector valued function that like square roots or fourth roots? Because you're not allowed to take the square root or the fourth root of a negative number. 0 is okay. Square root of 0, no problem, 0. So you would have to create an inequality where the radicand is strictly greater than or equal to 0 and solve that to get the values of t that would be okay. The fourth thing, are there any logarithms in your vector value function? Because you're only allowed to take logarithms like ln of positive arguments, like ln of 2 is okay, but ln of 0, not defined. ln of negative 2, So in this case, you would create an inequality where the argument is strictly greater than 0 and solve for that. And then any arc cos or arc sine, you'd worry because you want the argument to be greater than or equal to -1, but less than or equal to 1. Now, here's the hard step right here. This is where students have a hard time, but you didn't have to do this in pre-calc. You have to intersect all of the individual domain sets and find common ground so that those intersection values are your final answer. Okay? So I'm going to do a couple examples and then call it, and we'll finish up next time. Letter A, I gave a real easy example, okay? So let's do each of these. ln of t, are there any restrictions? Sure there are. We have an argument here in the logarithm, and you need the t to be strictly greater than 0. Otherwise, you're going to get into the world of undefined. Now, what I like to do is I like to graph this on a number line. So here is the t-axis, pretend. Here's 0. And if I were to graph this, I would put an open bubble on the 0 because we're not including the 0. And then anything larger than 0 is good. So I would shade it in red. Okay. Now, what about the middle component? Well, he doesn't have any restrictions on his diet because he's not in a denominator. It's not a square root. So he can eat everything. He eats the whole entire number line. So if I were to graph him, here's the t-axis again. I just shade in the whole thing. That's right. He eats everything. He's happy. Oops. Shade in the arrows too, because he can eat whatever he wants. Fine. Now, what about the last component, the square root of 1 minus t? Well, that's a problem because you don't want the 1 minus t to be negative. So what do you want? You want the 1 minus t to be greater than or equal to 0, and then we're happy. If you add t to both sides, you get the answer. But I'm going to rewrite this so I can see better. This is t less than or equal to 1, means the same thing. So if I draw another t-axis here and I shade in all the values of t less than or equal to 1, I have a bubble here, but I color it in because 1 is included in the set. And then less than means shade in all the numbers to the left, oops, including the arrow because it goes on forever and ever. Now, here's the hard part. Can you imagine all three of these number lines collapsing into one number line? What values of t would be all three colors at the same time? Which values of t would be red, blue, and green? This is the hard part because you want to take the intersection. And I claim it won't include the 0 because that wasn't shaded in the red. But it will include the 1, so I'm going to put a bracket. So this vector valued function is very restricted in his diet. He's only allowed to eat values of time t that lie between 0 and 1, but not including 0. So sometimes you may see this t is an element of, that's an epsilon, that means t is an element of that interval. And this is interval notation. And yes, you have to know how to do interval notation as your final answer. Okay. I don't want to see your final answer written as an inequality. Like this is the correct answer, t strictly greater than 0, less than or equal to 1. Sometimes MyLab Math might let you write it like that, but sometimes it may ask for interval notation. So know the difference, okay? They're both the right answer. Okay, I'm gonna do one more quickie problem and then we'll call it. Letter B. How do I do letter B? Oh my goodness. First component, absolute value t plus 2. Does that have anything to worry about? Look at my list. No, absolute value, don't care. There's no restrictions on this first component's diet. So what does that mean? He eats everything. So if I were to draw a number line for him, I'm just going to shade in the entire t-axis. He eats any number he wants. Fine. How about the second component? Uh-oh, we got a problem. Why? Well, t is in the denominator and you never want the denominator to be equal to 0. So here's what I need to do. I need to solve this equation for 0. And then whatever I'm going to put question mark. When does this equal 0? And whatever the solutions are, throw them out. That's what he can't eat. Now, this is a quadratic equation, and I hope you remember to solve quadratic equations from your algebra days. This particular quadratic equation is easy because I chose the numbers in such a way that it's factorable. So I'm going to factor it, t minus 3, t minus 5, and then apply the zero product property. If something times something is equal to 0, the zero product property guarantees us that we can set the individual factors equal to 0. And then I'm going to solve for t and I get 2 answers. Are these the answers? No. Remember, this is what we don't want. We don't want these numbers because they would make the denominator go to 0. So on the number line, what I'm going to do here, 1, 2, 3, 4, 5, is I'm going to sketch or shade in the okay numbers for this second component. I'm going to put an open bubble on the 3. 3 is not okay. I'm going to put an open bubble on the 5. 5 is not okay. But anything in between 3 and 5 is okay, like 3.1 or 4. Oops, doesn't stay when I do this. And then any numbers larger than 5 are okay. And any numbers less than 3 are okay. So I got to shade in all these. Oh boy, it's not staying. You get the idea. Trying to shade it in and it keeps going away. Okay, finally, the last component, square root of t plus 2. You have to worry. Why? Well, because you got an even radical and you don't want to take square root of a negative number. So what do you need? You want t plus 2 to be greater than or equal to 0, and you're happy. So we want t to be greater than or equal to negative 2. So if I do another number line here, line up your zeros, negative 2, you'll put a bubble on there, but it can be filled in because negative 2 is okay. It's in the set, and anything larger than negative 2 is okay. Now, here's the hard part. Intersect the 3 sets. This is the hard part. Imagine all 3 of these number lines collapsing into one number line. It'll help you a little bit. What values of time t are green and blue and red at the same time? This is hard because I claim you got to have a lot of answers. You're going to have bracket,
Would just be -2 up to 3, not including 3, and
Good.
then 3 to 5,
union,
or
5. Very good.
including 4 and then not including 5, and then to infinity.
Yes. So you have 3 different intervals all together. You use union symbols to take the union of all 3 of these chunks of the number line. And there's your final answer. That's nuts, isn't it? But that is the intersection of all these sets, these 3 components domains. You have to take the intersection to find the overall domain for your vector valued function. Pretty fun, huh? That doesn't involve any calculus, but it's cool.
Wait, why did you change the sign of 2 again?
Why did I change what?
And the y, yeah, in the y, what's it called?
Okay, in the y component,
Yeah, y component. Yeah.
remember.
Oh
that-
no, I'm sorry. I must be mistaken. I was looking at C.
Oh, we haven't done that one yet. I'll save that till next time.